The next talk is by Yuriy Reznik. He's a fellow at Brightcove, and he will be talking about video coding and delivery at scale. Alex? You still have the mic?
Yep. And you can probably hear this loud and clear.
Okay, this should help. Can you hear me? Okay. Thank you very much. And as it was mentioned, I'll talk about video coding and delivery at scale. And of course, the topic will overlap quite a bit with some previous talks. And I'll try to skip some things that are overlapping in that sense. But before I start, let me say a few words about Brightcove and the kind of scale that we'll be talking about. And so the company is in business since 2004 with headquarters in Boston, Massachusetts. We have about 500 people. And we serve about close to 5,000 clients in over 70 countries. And we push about 3 billion of streams every month. If you count this per second, it boils down to about 1,000 encoding jobs being launched every second. It's a scale of some sort. And to make things merrier, it's happening in all places of the world and using all sorts of computing resources. And we're delivering to all sorts of networks, delivery devices, and so on and so forth. So it's pretty challenging. Now, the leading product that we have is called VideoCloud, and this is end-to-end content management platform. The users of VideoCloud can upload content to the system. They can manage it. They could transcode it to certain targets, and they can push it to plurality of players. So players are embedded. They're part of the platform, and part of the platform is also analytics, where users can see statistics of how streams are being delivered. They can optimize delivery based on the statistics. They can monetize it by using SSAI and client-side advertisements as well. So it's a pretty powerful and flexible platform. And if we look underneath, the key building blocks are shown here. So the request comes from publisher. It's usually it's a cloud-based workflow. It could be automated. It could be job requests pushed to HTTP address, or it could be manual, this user interface where user can upload specific content and say what to do with it. Then it goes to ingest module. After that, the content is transcoded by our cloud transcoder, which is called Zencoder. It's, by the way, available as a standalone module as just cloud transcoder, but it's used internally within VideoCloud. After content is transcoded, it's going to our dynamic delivery system, which includes multiplexer, DRM, client-side and server-side insertion mechanisms, and then it's pushed to players. And finally, players report results to analytics module, and there you could see statistics and figure out how effective or efficient your system is operating. Now, we recently added one more piece in this system, which is called CAE, context-aware encoding profile generator, which optimizes system end-to-end. When we generate profiles, we take statistics from analytics, so we know distributions of networks and characteristics of delivery context as streams being pushed to clients. We also receive parameters and constraints from users saying what range of bit rates to use and so on. And based on this plus characteristic content itself, we generate profiles, and that creates plurality of those streams, recipes for encoder to use to generate streams. So, but the fundamental point, it's really operating as end-to-end optimizer. It looks not only at property of content, but also at delivery context, and which makes it very powerful. Now, main challenges in building, operating, and optimizing the system. Of course, number one challenge is scale. It has to work at millions of concurrent streams. We have to use clouds and plurality of clouds, and we need to manage all those. Reliability, of course, comes equally as important. Things just have to work, and they have to work not only in case where they would work normally, but also when, for example, input content is broken. We need to fix it for users if we can fix it, or when some segment of cloud goes down, we need to switch, operate with resources around. We need to survive. And everything has to be redundant, fault tolerant, and so on and so forth. So reliability is paramount priority. Of course, we need to reach almost all devices in existence. And of course, that makes problem challenging, because those devices include some legacy TVs, include some Blackberries, includes all sorts of things. And to make things merrier, now we have to deal with also some new formats. We have new codecs, we have plurality of DRMs, we have plurality of HDR formats coming. It makes things even more challenging. And bottom line, of course, everything needs to operate with reasonable costs, and everything needs to be delivered at high quality. So this is few challenges that I see from engineering perspective. There are probably even more challenges at business level, integration level, but let me just focus on a few of those, and that will be enough to fill the remaining 20 minutes. So, but let me start with something that I think lots of folks in the room will resonate to, which is what we do when we have multiple formats, devices, and we need to support all of them. If you just need to support, for example, one codec, one delivery format, and one DRM system, your system could be very tiny. It's a very compact and elegantly designed system. But once you start adding support for many of them, it naturally grows. It becomes more complicated. And as I said earlier, not until recently we were just enjoying living in SDR world, where the world settled at BT709, and it was one single color space, one gamma. Everything was clear and understandable. Now we have about 10 different HDR formats. And just to name some big ones, of course, there is HLG, there is PQ10, there is variants such as HDR10. There is about 8 flavors of Dolby Vision. There is HDR10 Plus, there is SLHDR1, there is also SLHDR2, and this list is actually growing. With codecs, we have, of course, H.264, which was ubiquitous, but then HEVC is more efficient, right? So it makes sense to support it. VP9 is also more efficient. It's available on different platforms, so it's good to support it as well. AV1 is coming. Of course, VVC from MPEG, JVET is coming too. So they're all nice, but adding all of them adds complexity. And similarly with different DRMs and different delivery systems. HLS has grown to have 7 versions at this point. Dash has multiple operating points and profiles. We still need to support smooth. And why would we support smooth after Dash came around, which is supposed to unify everything? Well, because there are TV sets and game consoles that could only work with smooth and play ready and nothing else. And if you want to target them, you have no choice. And there are a bunch of devices that can only support progressive download, so that literally adds to the space. And if we just make a thought experiment, and by the way, this is the matrix of different DRMs and different client devices of support. It's courtesy of Cast Labs. They had a wonderful picture showing just complexity of just that last piece of delivery. So if we make a thought experiment, let's assume that we have a piece of content, and it needs to be encoded, say, at 7 different encoding layers with 7 different resolutions and bit rates, which is pretty typical for ABR streaming, right? Then we have 3 codecs. Why? Because H.264 baseline is actually a different codec. it has different rate distortion characteristics. If you want to target those devices, you better encode all breakpoints at H.264 baseline. Then of course, there is H.264 with main high profiles, and then there is HEVC, which of course will work better at smart TVs and Apple devices. So there are 3 codecs, and we need realistically 3 DRMs. Why? Because to support Apple devices, we would need to have FairPlay. To support TVs, we will need to have PlayReady, and for Androids, we will need to have Widevine. Right, and we will need 3 formats, because HLS will be needed for iOS, Dash will be needed for TVs and some Android devices, and for legacy devices, Progressive will be only things that will work. So that all boils down to 7 times 27, 189 streams, just to send one piece of content. I think we're done here. This is just not practical, right? So how to solve it? There are a few tools, and some of them are new and some of them existent, but you really need to have a combination of them to solve the problem efficiently. First is just-in-time packaging. Instead of packaging one stream for HLS and encoding a single stream and storing as HLS stream and another for Dash, you could do it dynamically, and you could save storage and CDN cost of doing it. You could avoid replications of streams for different DRMs. DRMs could be added dynamically, especially if common encryption is a commonality layer that's used across all of them. Second, you can't use just-in-time packaging without device detection. You need to know the capability of what device you're streaming to and what the capability of this device is. You need to recognize what it is, and you need to target manifest accordingly. Now, to target manifest, you also need to set up certain rules. You need to set up, for example, for device X, you need to know which range of resolutions, which codecs it could support, which range of bit rates it will be able to decode efficiently. So here comes rules engines. And to optimize a whole package of different encodings, you need to have a multiple codec profile generator that effectively allocates bit rates and shuffles them across different coding standards to solve problems in effective and optimal way. So I'll talk a bit about all of those. But first, let me talk about a combination of first 5 tools that I mentioned earlier in Brightcove VideoCloud, and this subsystem we call dynamic delivery. So what is happening here is that, of course, we are using just-in-time packagers. Just-in-time packagers are activated when streaming clients are sending requests to retrieve a content, and CDN reports miss saying that the content of this format is not existent, and then we activate our system. We regenerate this content on the fly, and then we push it to CDN at that point. As a part of this process, we also generate manifests. As we generate manifests, we, of course, first recognize what kind of device it is. We, of course, apply a rule engine, and we, of course, could use preferences from operator to say how to generate those manifests and how to target delivery for the system. Now, of course, the input for just-in-time packagers and manifest generation are internally stored data, which are stored in internal formats coming from the encoder. Not only encoded streams are pushed, but also metadata that are sufficient to describe plurality of possible retargeting scenarios that we will need to support by just-in-time repackaging. And so this system is effective. It saves, reduces the number of formats that needs to be generated, and it reduces it only to the set that is actually being used, because it's only one client request, for example, a stream which is Dash with PlayReady and with other permutations with certain codec parameters, only then we will generate it. And so it reduces this combination, it reduces CDN storage cost, and it reduces, of course, bandwidth costs as well, as you don't need to transmit things internally in additional formats, as happens with legacy systems. Now, let me switch gears to video transcoding and And here I will talk about a few other things that we do to achieve things at high scale and achieve high quality. So there are two generally different regimes of encoding. In broadcast world, we used comfortably to live with single rate transcoding. There is a single stream that needs to be transcoded, and there is single output that needs to be produced. They have different formats. They might have different resolutions, but it's one-to-one mapping. Now, when we encode for ABR, same content, same input stream should produce a plurality of outputs. Now, this plurality of outputs is usually called ladder or profile. Some people call it recipe. But it's basically a set of coding parameters that needs to be, and preprocessing parameters that needs to be applied to arrive at each of those delivery streams. This set of parameters needed to be generated, so this one important step is going to be ABR ladder design. Now, when we go from input format to output format, there might be need to do format conversions, there might be need to do certain video processing operations, so those are also important, and of course there is encoding operations which we'll talk about. Now, when we move things in cloud, things get a little bit more complicated. First of all, if encoding was, transcoding was previously reduced to operations between decode and encode, then since things done in cloud, things needs to commute in formats that are self-sufficient to describe what the content is. So the input needs to be maxed in certain file formats that is describing the properties of format completely, and the output needs to be maxed in certain containers that is self-sufficient. So this adds two steps of demax and max. It might not be final delivery max, but it might be maxed to some intermediate representation, for example. Now, the other thing that happens in cloud is that, of course, you don't run a single transcode. You run it in thousands or millions of instances that you could allocate. And managing such instances is an art of itself. These instances could be provisioned ahead of time. They have certain lifespan. There are costs associated with provisioning instances. There is also, and it's actually quite sophisticated. With Amazon AWS, there are also spot markets where you could buy instances which were used by somebody else and now being resold at a fraction of the original price. And so it becomes more cost effective to use fraction of this time acquired at the spot market. So part of the cloud orchestration engine is to kind of listen to what's available and do economic optimizations to acquire resources, provision them, and make them available for transcoding tasks at the time when they are arriving. So the distribution of job becomes important. Of course, everything needs to be driven by Cloud API. Of course, there should be means for monitoring, and there should be means for ensuring reliability and minimizing the cost. Everything needs to be redundant and fault tolerant. Distribution of work, actually, Alex was giving a very good talk about doing things in segments, which helps a lot, but there are actually more things that can be done. So first of all, instant level parallelization applies. Instant level is the types of parallelizations that you would do on a single computer. A single computer might have multiple CPU cores, it might have multiple GPUs. So using coding internal tools or internal means such as slices, styles, wavefronts, sometimes GOPs or micro-GOPs, are all means for finding out slices of jobs that could be allocated to all those resources that are available within computer. And of course, folks like Multicore were experts at using this, as well as many other vendors of just basic coding algorithms. They're usually well optimized to operate effectively on a single computer and using resources that are available on single computer. So that's applicable to cloud as well. The only difference is that in cloud you will be dealing with instance that's allocated dynamically with particular profile. Now, segment level parallelization is when you take a video and you split it in chunks, and then you allocate it chunks to different instances. That helps to achieve the parallelization, but there are certain cons to this. There are issues such as challenges with ensuring consistent quality, HRD issues, as Alex was mentioning. So there is a bit of art in doing this. And the other thing, it only works for VOD. For live, doing things in chunks will only add latency, and latency is usually something that close to heart of live services, and nobody wants to sacrifice. Stream level is kind of more straightforward. You take a single stream and you send it to an instance. It works in most of cases, but there are also some caveats. For example, if you encode for ABR, it's more effective to send to instance a whole package of streams and allocate probably more powerful instance and encode all those streams simultaneously, as there is certain gains that could be achieved by processing them jointly. So that covers parallelization. There is quite a bit of art, and of course we had lots of fun solving all those things. Actually, the encoder took about 5 years to develop and about 10 years to optimize and get it to the scale at which it is today. Now, of course, everything is driven by cloud APIs. As example, I'm showing the encoder cloud API. It's basically, to start the job, you send HTTP post to a URL, and in job request, you just provide JSON file saying this is an input, and then this is an array of outputs with parameters of each output that you would want to produce. You can also say notifications, which will mean this is a listener where you will send the results of job when it's completed. For example, you could send notifications that job is accomplished and it's all successful, or there were some issues with it. Now, there are, of course, lots of things to be taken into account when the system is designed and optimized. I mentioned some of them. But the most important, if we're talking about high quality that needs to be delivered by a cloud solution, there is no magic here. You need to run high quality encoder. Your encoder by itself needs to be good. So all the science that goes in optimizing rate control, all the science that goes in pre-processing, all science going in setting codec constraints and optimizing ladder designs become applicable. I'll talk very briefly about some of this. For example, pre-processing is super important, especially if you have to operate with broken streams or streams which, for example, were progressive, but somebody encoded interlace, or they were interlace, somebody encoded progressive, or there were some cadence and somebody encoded with different cadence. There is a whole permutation of possible human errors that people can make, and they usually make them in practice. And of course, what do you do with this? So first thing that needs to be done in every reasonable system should be content analysis that actually tries to understand what this thing is and looks and compares it with metadata, because metadata might not say what it is. And based on this, you then apply tools such as artifact removals, temporal resampling, color space conversion, spatial resolution conversion, frame rate conversion, and so on. So that's a must. And there is lots of art, and I would say black art, in designing some of these algorithms. And this is key to have a successful and effective system. Of course, another is understanding and measuring quality. There are, of course, many metrics out there, MSE, PSNR, SSM, FSIM, but they all measure only codec noise. And they don't, and these are full reference metrics. They're not gonna say what would be the quality of video encoded at different resolution. So to translate from one resolution to another, you need to use something more sophisticated. And there are things like visual difference predictor of Scott Daly. There is a Tektronix PQA, which uses old Sarnoff metric. There is, of course, now SSM plus from SSM Wave. So these are more advanced metrics. They're definitely better. But the other thing is fundamentally none of these metrics is perfect. And this is the reason why. They all try to reduce quality assessment to single number. But quality assessment in human world is never a single number. We're dealing with population of viewers, and each viewer will have a different opinion. So you will really have a distribution of opinions, and the only thing that one can infer from a single number is the probability that certain number of viewers will think that this quality is above or below certain threshold. But it's not going to be an absolute number by itself. So basically what I'm saying is that there is an extra layer of science that each encoding company is practicing and using in their internal measurements and their internal art of setting quality targets. Now, choices of resolutions, of course, in many systems, the set of resolutions are predefined, but if you have many resolutions that are allowed, such as, for example, in DVB dash recommendation, well, then the more resolutions are available, the merrier. Why? Because at each resolution, you might have a concavity gap in a quality rate space where if you add extra resolutions, there will be region of rates where this content will look better. But of course, you really need to stick to what's allowed, what's supported by devices. And there are a few extra interesting things, such as a range of feasible resolutions. I'm not going to talk about it, but if you look at this slide, it's actually going to be fun to look afterwards. Now, on setting codec constraints, this is another thing that belongs to domain of art to some extent, but some things you just have to do because otherwise there will be clients that's not going to receive streams and things going to look right. For example, you can't stream videos encoded with CRF or unconstrained VBR or constant QP type of encoding. The bit rates are going to fluctuate like crazy. And if you're sending a set of streams that coded at set of bit rates and client relies on those bit rates as their input to which rates will be effectively available, when it fluctuates by factor of 100, they're going to get confused. At some point, clients starts rebuffering or it will pick a suboptimal stream. So streams need to be constrained capped VBR. And for most of recommendations, the cap is limited to about 10 to 35% above bitrate. In some recent HLS guidelines, they say you can go up to 100, but it's still 100, not 200 or 1,000, as bitrate might fluctuate in practical cases when you run unconstrained VBR. GOB length, of course, encoding should be done at the shortest length that you would use later for SSI or for delivery. And for example, if there are multiple possible delivery scenarios, such as content could be segmented at 4, 6, and 10 seconds intervals, and the safe shortest GOP size that you should use for encoding is going to be greatest common divisor of this, which is 2 seconds. And that's going to satisfy all those. Profiles and levels, of course, baseline must be supported. There are still devices that cannot support. High is better for 1080p beyond. Levels must be set such that they playable on devices. B-frames must also be constrained. Most set-top boxes can only support 4 B-frames for H.264 and up to 4 reference and 3 B-frames. So now optimizing encoder ladders, it actually could be posed as a mathematical problem, but instead of diving into specific mathematics of this, I would say that it actually works. And we have solutions that works today at pretty reasonable scale, as I mentioned earlier. It's called context-aware encoding. It's available as one of few choices of input profiles as people upload content, or actually operators could specify custom constraints where they would say dynamic profile options, and these are the ranges of renditions, maximum resolution, maximum bitrate, and so on and so forth. They actually also can provide characteristics of networks and devices that will be reducing. We have usage parameters, elements of bit streams, so it's pretty advanced. And this is an example how it works. So on the left, we have a static profile, which has 8 renditions going from 270p to 1080p. And on the right, we have dynamic profile or CAE profile generated for same content. Only 4 renditions, and that was sufficient to cover it. At top level, we save about 36%. If we're somewhere in the middle, we actually deliver more pixels. For example, at about 700 kilobit standard profile at 900 is using 360p. We actually delivered 432p at less bit rates in the middle, and it covers the entire range with reasonable steps, with reasonable granularity. So it really saves a lot of bits. It saves number of renditions, and since it saves number of renditions, it saves cost. And not only of transcoding, but also transmaxing. And if we remember at the beginning when I said that it's actually going to be multiplied by number of DRMs, number of delivery formats, and so on, this simple reduction in number of encodings actually goes a long way of reducing your operation costs in the whole system. So summary, there are lots of things, fun things that could be done to design modern era delivery system. Dynamic packaging is super important, mass scale transcoding important, as well as other things such as clients, monitoring, analytics. And one, of course, can have lots of fun designing it all or pick existing solution. And if you like to try our products, these are the links which you could click and give it a try. Thank you very much.
Okay, thank you, Yuriy. So we can take 1 or 2 questions. Any questions out there? I know it's a lot of information that's been going on throughout the day. Okay.
In your encoding ladder design, where you showed reducing the number of levels, do you measure the least noticeable difference, the interruption that the viewer will see during one of those switches?
Well, if you think about just noticeable differences and you're trying to design a system that would switch to just, for example, 6 GNDs, we'll have system with hundreds of streams for each content. And it's going to be large number, and it's going to be same regardless of complexity of video. In this case, we use granularity limits that are imposed by system guidelines. For example, your bitrate should not jump by more than 100% as required by HLS, for example. And we also impose additional internal limits on resolutions, gap in resolutions by how many pixels you could jump from one step to another. And we tune system to the point where we think it operates as effectively as a system with existing standard presets such as HLS, recommended preset, and such. So it's going to be at the same or less level of disruptive difference as existing profiles. But we have parameters called granularity. You could tune it to very low level, and it will let you achieve what you probably want to achieve as well.
All right. Thank you, Yuriy.